Let's revisit the question I asked in our confidence interval video. Do students at UT incorrectly estimate the height of the UT Tower? Now, I have a piece of information I didn't actually share last time. I do know the correct height of the UT Tower. The tower is actually 307 feet tall. Using the information I collected from my class, can I now make a statement that all UT students do or do not estimate the height of the tower correctly? Absolutely, I can. This process is called hypothesis testing. There are several ways to accomplish hypothesis testing, but the first step always starts with having specific hypotheses to test. When we do testing, we will write a pair of hypotheses. The claim we are testing is the null hypothesis. This is typically some sort of claim of no difference. It's abbreviated as H0 or HO. Because we will use this hypothesis to make a claim about the population, we will use the mu symbol in our hypothesis. Remember, mu stands for the mean of the population. For our test, the null hypothesis will be mu equals 307, or the population mean guess for all UT students is 307 feet, which means they guessed accurately. We will also write a competing and opposite hypothesis. This is that there is actually some difference. For this test, our alternate hypothesis then is that students incorrectly estimated the height of the tower. To write this, we would say mu is not equal to 307, or the average estimate from UT students is not 307 feet. Now that we have these hypotheses, we need some way to make a decision about whether the null hypothesis is true or not. First, we will start by calculating our test statistic. This is a value called a t-statistic that represents the standardized value of our sample mean. This is similar to what we did with z-scores. We discussed the formula for a t-statistic previously as well. For this test, we will take our sample mean, subtract the mean from the null hypothesis of 307, and divide by our estimate of the standard error, using our sample standard deviation and sample size. For our test, we get a t-statistic of 1.80. Now we have to decide what that t-statistic tells us about the null and alternate hypothesis. When we do a hypothesis test, we will always have to make a decision about whether we find enough evidence to state that there is a statistically significant difference between our population mean and the value we are comparing to or not. If you return to our null and alternate hypothesis, it means that we're looking for evidence to reject the null, that the values are the same, in favor of the alternate, that the values are different. Just as we decided during the confidence interval calculation, we will again be making decisions that should commit us to only having a 5% chance of making an error. We will talk in more detail about that error later. So let's think about our t-distribution now. When we calculated our t-statistic, we subtracted our sample mean minus the value from our null hypothesis and then standardized by dividing by our standard error. So our t-statistic is telling us how many standard errors away from the comparison value we are. If our sample mean is very close to or equal to our null hypothesized value, we will expect to find a t-statistic close to 0. If our sample mean was very far from the null hypothesized mean, then the resulting t-statistic would be further out in the tail. We set the boundaries here, marking off the most extreme 5% of the distribution. The value marking that off is the 1.99 and negative 1.99 that we looked up when we were working with our confidence interval, and that value was based on our degrees of freedom. These values then therefore separate out the center 95% of t-statistics from the extreme 5% in the tails. Look at our picture. For our t-statistic of 1.8 that we just calculated, it is not in that extreme 5%. Instead, it's closer in towards 0. We will take this as a sign that while our population mean may not be exactly 307 feet, we don't have enough evidence from our sample to state that the population mean is extremely different from 307. In other words, we have a difference between our sample mean and the comparison, but it isn't enough to lead us to conclude there is a statistically significant difference in the population. Let's talk about the process we just went through. We actually went through the 4 steps of hypothesis testing. We first set up our hypotheses. Second, we chose a significance level. This is the part where we decided to select 5% of the distribution to be our rejection region. We only know how to do one type of t-test for now, so our choice of test was easy this time, but we will learn more in the future and this step will be an important one. And we checked our conditions for our test last time and confirmed that we had a good sample and it was large enough to make conclusions from. Third, we computed our test statistic and compared it to our critical value. This told us what decision we could make with regards to the null hypothesis. Fourth and finally, we were able to interpret our results. We can conclude from our test that we failed to reject the null hypothesis and did not find evidence that UT students incorrectly estimate the height of the tower. What if we had found a large t-statistic instead, such as a t-statistic of -2.5? In that case, we would have made a different conclusion. If we had found a t-statistic in the extreme 5% rejection region, then we would say we actually did find evidence for a difference in the population. Setting up our distribution as we have, marking off that extreme 5%, we said that our tails should contain only 5% of possible t-statistics for a sampling distribution based on the null hypothesized mean of 307. So if we had a t-statistic that made it in the tail, it would only be there because there was a large difference between our sample mean and our comparison value. And having that large of a difference indicates that we could conclude based on our sample that our population mean must also not be equal to the value in the null hypothesis. This will be our standard procedure. We will set up the t-distribution with the critical values marking the tails or the rejection regions of our distribution. If we find our t-statistic is in the tail, we can reject the null hypothesis. This is evidence our sample mean represents a population different from our comparison value. However, if we find a t-statistic in the central region, it means our population mean might not be exactly the null hypothesized value, but it's close enough to not be considered statistically significantly different. In the next video, we will continue to talk more about hypothesis testing. If this process is confusing right now, don't worry about it. We will spend this entire unit repeating this process, and in statistics, repetition is often the key to understanding.